MPLS TE administrative weight. In this video, I'm going to talk about the administrative weight, the function of the administrative weight, and also how we can use the administrative weight. And finally, I will talk about the configuration and also verification of this feature about the MPLS TE. Let me first talking about the concept of the administrative weight. What is the administrative weight? Look at here. We have administrative weight in the MPLS TE tunnels, and we can configure the administrative weight for every interface. You know that in the IP routing, let me to talk about that. In IP routing, we have, for example, routing protocols, and we use routing protocols for finding the best path, okay? And every and each routing protocol, for example, RIP, OSPF, ISIS, or IGP, are using the metric for selecting the best path. You know that the best path has the lowest metric. You learn about this feature in previous courses. For example, you know that in RIP or routing information protocol, we are using the hop count as our metric. Or in OSPF, we are using the lowest total cost for selecting the best path. Or in ISIS, again, we need to calculate the lowest cost for each path, and finally the best path is the path with the lowest cost, okay? And here we can understand that in IP routing, in pure IP routing, we have only one metric, and that is the IGP metric. And IGP metric is different for different routing protocols, okay? After that, in MPLS TE or MPLS traffic engineering, again, you know that we are using one of the OSPF and also, for example, ISIS as the IGP. I talked about this, and you know that in traffic engineering, we can use only OSPF and also ISIS. We don't use the RIP or EIGRP or, for example, BGP, okay? The first question is that how we are selecting the path for tunnel. For example, when you are configuring the path option, okay, explicit, you know that in the explicit path option, as I mentioned before, as I configured before, only the administrator can choose the best path. This means that administrator should manually configure the path of a tunnel. But when you are configuring the, for example, path option, then dynamic, how TE should select the best path for the tunnel, okay? You know that the TE should consider the constraints of the links. For example, bandwidth requirement, or as you learned in the previous scenario, affinity, or some other features, okay? But my question is, if all of the requirement, okay, of a tunnel, of we configured in tunnel interface, are compatible for more than for one path, how TE should choose the best path? Look at here. Assume that in this scenario, we have between the R1 to R4 two paths, R1, R2, then for example R4, and after that R1, then for example R3, and then for example R4, okay? We have two paths, and these two paths are exactly same. For example, they have both bandwidth of for example 1 megabit per second, and also we configured a tunnel on the R1 tunnel with the bandwidth requirement of the for example 500 kilobit per second. Both paths are for example compatible with our requirement. How the TE should select the one of these paths, okay? Yes, maybe you say that we are using the, for example, affinity. Yes, about the affinity, we don't have any difference between these two paths. How TE can select the best path? Okay, let me to talk about one of the features that TE is using that feature for selecting the best path, and that is the administrative weight or TE metric. Let me to talk about it. Look at here. As I mentioned before, in IP routing, let me to review. In IP routing, we are using only the IGP metric for selecting the best path, okay? But in TE, okay, in MPLS traffic engineering, we have two types of metric. The first is IGP metric, And also the second is TE metric. Let me talk about these two features, IGP metric and also T metric. The T metric's other name is administrative weight. I will talk about that. But let me to say here, the TE metric is administrative weight. Because of that, here we can say MPLS TE metric or MPLS TE, for example, administrative weight. Both of them are same. Okay, let me to talk about the TE metric. What is the TE metric? Look at here. In this scenario, as you can see, we have fast Ethernet between the R1 and R2, and the protocol we are using here is the OSPF. You know that in OSPF, cost of the interfaces can be calculated with this formula: 10 to the power of 8 divide to the bandwidth of the link. Okay, because of that, for fast Ethernet, the cost equal to 10 to the power of 8, again 100 megabit per second, because this is the, for example, fast Ethernet. 100 megabit means 100 million. The result is equal to 1. This means that every fast Ethernet links in the OSPF has cost of 1. Okay, let me to calculate from the pass metric from R1 to R4 with both of these paths. For example, in this example here, we can write it here, R1 to R2 to R4. The metric of the first pass is 1, and the metric of the next pass again is 1. Okay, because both of them are fast Ethernet. And finally, okay, this is the bandwidth of the links is 100 megabit per second. And finally, we have the total cost of the tree to the loopback 0, because here we have one loopback 0 and the loopback 0's cost is 1. 1 plus 1 plus 1 is equal to the 3. Also, from the lower pass, again, we have the same condition. Okay, here also is the bandwidth 100 megabit per second and the cost is 3. This means that we don't have any difference about the bandwidth in these two passes. Because of that, we don't use this feature. Now you can understand that the MPLS traffic engineering should calculate the metric, but because here we don't have any change, don't consider these cost values, because the MPLS TE doesn't see any change, any difference between these two. For example, pass about the metric. The metric doesn't have any effect on the pass selection. But let me talk about the metrics in this pass. Look at here. You know that until now, we talked about only IGP metric. Let me to say that every pass, every interface on the MPLS traffic engineering has one another metric, TE metric. And these two metric are independent metric. This means that for one interface, for example, in the router 1, when you have fast Ethernet 00 and the IGP metric of the fast Ethernet 00 is 1, we have another metric for this interface, TE metric. By default, TE metric equal to the IGP metric. Because of that, TE metric and IGP metric by default are equal, and we can change both of them. For example, you know that in the OSPF configuration, we have a command IP OSPF cost, then cost. You can change the cost of OSPF with the IP OSPF cost. Or in ISIS, you can change the metric of interface with the ISIS metric command, for example. Okay, but here we have another type of metric, T metric. You can't change the T metric with the, for example, IP OSPF cost. But let me to say that by default, the value of the T metric is equal to the IGP metric. Okay, until now, we learned about the T metric, another type of metric that is available on each interface. Now, let me to say for the first time that when we are configuring the MPLS traffic engineering tunnel, okay, the MPLS TE uses only T metric, okay, by default. By default uses T metric for calculating the best pass. This is the default behavior. Maybe you say, why we didn't see TE metric until now? Because the TE metric by default is equal to the IGP metric. For example, if you configure this scenario, R1, then R2, then R3, after that R5, and after that we have, for example, another links. This is R1, R2 to